Hello, my name is Matthew Miller, and this is my real-time systems final capstone. I've built a real-time avionics UAV system that processes asynchronous radar interrupts with strict bounded latency, designed to demonstrate deterministic hardware-in-the-loop timing for an electronics test engineer role. Alright, so here's the system running live in the Wokwi software here. I have a background load of 4 tasks competing for the CPU to simulate heavy system noise. When I trigger a radar pulse via this GPIO button, the system registers an interrupt. As you can see in the terminal output, the critical bottom half task wakes up and logs the beacon update with a highly deterministic latency of around 2400 microseconds, successfully preempting the background noise. Alright, so if we look up here, the architecture relies on the top half bottom half pattern. The hardware ISR, or top half, is extremely lightweight, executing in about 15 microseconds just to acknowledge the hardware trigger. It then uses a direct task notification to wake the bottom half FreeRTOS task, which runs at priority 12. Looking at the task table here, I calculated the worst case execution times for the background load tasks and the critical beacon task. The total CPU utilization is 0.38 because since this is well below the rate monotonic schedulability bound of 0.78, the math proves that this system is guaranteed to meet all its deadlines safely. So let's go back to this Wokwi simulation and let's comment out this right here. So to demonstrate what happens when real-time principles are ignored, I am intentionally injecting a fault by removing the port yield from ISR macro. Let's comment that out. Without this explicit yield, the context switch, here, let's restart that. The context switch is no longer immediate. The interrupt slightly hands control back to the idle task. If we look at the timestamps in the terminal now, it's running once again. Alright, so you can tell, if you can see the high priority task is stranded for up to 10 full milliseconds, waiting for the system's background tick timer to naturally force a scheduler evaluation. The system's determinism is completely broken. So you can see right here, the UAV beacon notification is at 16,870, and the radar 10 microseconds later is getting that update. That's unacceptable. Looking forward, this exact architecture scales directly to production environments like hardware in the loop testing at SpaceX. When testing avionics flight hardware, the automated test equipment must act as a hard real-time system. If test software suffers from the tick-align jitter I just demonstrated, it could falsely fail perfectly good flight hardware. By manually managing priorities, enforcing explicit yields, and validating worst-case execution bounds, this project demonstrates the strict determinism required for high-stakes aerospace testing. Thank you.